Hey everyone, Morgan here. We are back with the Thermochemistry Lectures for AP. We're on page 7 of 16 today, and we're going to be talking about phase changes. Now, there are 6 phase changes that we talk about, just limiting ourselves to the phases of solid, liquid, and gas. We're not going to deal with Bose-Einstein condensates at all. We're not going to deal with plasmas. They would basically be classified as gases anyways. Okay, so when a solid turns into a liquid, we are going to call that melting. And when a liquid turns into a gas, we're going to call that boiling. Please do not call it evaporation. Evaporation has some strict definition that we'll be getting to in chapter 11. Okay? A gas going back into a liquid is condensation. And a liquid turning into a solid is called freezing. So there are 4 of the phase changes. Well, what are the other 2? Well, a solid can go all the way over to a gas, and a gas can go all the way to a solid. This would be sublimation, and gas to solid is going to be called deposition. All right, so we should know those names and we should use them properly. All right, let's talk about the molecular level. Let's get down to the particulates again. What happens when you heat something? Basically, the molecules move faster. Kinetic energy is going to be transferred into what you are heating. And the temperature of what you are heating is going to go up. That's important to know. What's not happening? Chemical change. We're not talking about chemical change here. We're just talking about phase change. Okay? Now, we have a dilemma when we talk about heat and phase changes. If I put a pot of water on the stove and I turn the flame on underneath it, it gets hotter. And then it starts to boil. But while it's boiling, it stays at a constant temperature. Now, strictly speaking, just in terms of definition and not what's actually going on, if the temperature's not changing, the substance, the object, is not being heated because there's not a temperature change. But we know very well that there's a flame from the stove underneath that pot of water and heat's being transferred. So because of this is just a semantic argument, not a chemistry one, we need to come up with some new definitions. So the temperature stays the same. During a phase change. Okay? So that new type of heat, and again, just think about it. If Q equals mc delta T, and delta T is equal to 0, Q is equal to 0 by this definition. So the new type of heat that will allow for there to not be a temperature change is going to be called a latent heat. Okay? So some people say heat that causes a phase change. I've also heard heat that's associated with the phase change, or heat that does not cause a temperature change. Okay. Latent means hidden. So this is like hidden heat, heat that is not doing its normal job, so to speak. Now, there are some latent heats that we have named, like the heat of fusion. Delta H naught fusion. It has a very strict definition. The heat required to melt 1 mole of a substance at its normal melting point. So we don't have to heat it up to get to the melting point or anything like that. Okay? Now, the next one is called the heat of vaporization. Delta H naught, and most of the time we just say VAP for vaporization. Now that is the heat required to boil 1 mole of a substance at its normal boiling point. Now, before we go on, these are really the only 2 definitions I need to know. There's 6 phase changes, but these can give us all 6. So this is for melting, okay? That's going to be endothermic, by the way, because you have to heat something to melt it. But what about for freezing? It's the exact same value numerically, except we're taking it out rather than putting it in. So we just put a negative sign on the number. Same with the heat of vaporization. To boil, endothermic, heat goes in. But for condensation, you have to take the same amount of heat out. We just put a negative sign on it. Now, how about like sublimation condensation? Simple. Delta H naught sublimation equals, delta H naught fusion plus delta H naught vaporization. Okay? And if we wanted one for deposition, we'd take the same number, but we'd put a negative sign on it. Okay? So really we only have to know these 2 definitions. Now, values. Let's go on to page number 8 here. You really don't need to know the values of any of those. They will always be provided for you in tables. Okay? So, a little bit about heating curves. And you did a lab on this last year. It was an at-home lab, actually, doing it in the kitchen. Okay? So, what this looks like is basically a graph that goes like this, like this, like this, like this, like that. And over here we're talking about temperature, and over here we're talking about time. Now, these 2 plateaus represent melting and boiling. So, if we're talking about water, very specifically, ding, 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 that temperature would be 0 degrees Celsius. And that temperature would be 100 degrees Celsius. So you take a solid, you heat it until it gets to 0 degrees. That's, an ice cube, a big block of ice. Heat it up to 0. It will melt, and it'll stay at the same temperature while it's melting. Then, that liquid water will be heated up, but you can only heat it up as high as 100 degrees Celsius. Once it gets to 100 degrees Celsius, what's it going to do? It's going to boil. Now, the steam can then be heated to a higher temperature, but only once it's been turned into steam. Okay. Now, Let's start a couple simple math problems just to get the ball rolling here. Okay? How much heat is required to melt 50 grams of ice at 0 degrees Celsius? So I look up here and I'm like, okay, what is the heat of fusion for water? 6.01 kilojoules per mole. Okay, that's fine. I'll take my 50.0 grams, I'll divide by 18.02 grams per mole, and this equals 2.77 moles of water. Q equals MC, or equals M, or N could even be used, times delta H naught fusion. You can say it pretty much either way. Now this equals 2.77 moles times the heat of fusion for water, which is 6.01 kilojoules per mole. Moles cancels, and that is about 16.6 kilojoules. It takes a lot of energy there for that phase change to happen. Now, you can also do the same thing for 75 grams of benzene. Now, when I said at 0 degrees or at 278.6 Kelvin, what I'm implying is, and if you look here for benzene, 278.6 Kelvin is the melting point, okay? You don't have to do anything except the phase change. So 75.0 grams divided by, and for benzene, it's 78.12 grams per mole. Okay, and that comes out to be about 0.96 moles. Q equals MC, which equals 0.96 moles, multiplied by, and I look up the heat of fusion, it's 10.59 kilojoules per mole. Moles cancels, and this equals about 10.2 kilojoules total. All right, so I think that's pretty straightforward and stuff that we've looked at previously. So what I'd like you to do is actually attempt the next page and then come back and watch me go through it once you have answers done there. All right, this is Morgan signing off.